Hello everyone, this is Group 3 Electrocardiogram Design Presentation. Before we talk about our design, I would like to briefly introduce what is electrocardiogram machine or ECG machine in short. ECG machine is a very popular medical device in hospital that can measure heart rate and generate electrocardiogram to illustrate the heart activity to help doctors to diagnose patient. This machine works by attaching electrodes on patient's chest and limbs to detect the biopotential signal from electrical activity of the heart. Furthermore, there are many different types of ECG machine and they serve different purposes. For example, 3-lead ECG machine is a simple medical device with only 3 electrodes and is often used for short-term monitoring or used in emergency situations. Its advantage is fast and easy to set up, but it only provides limited view of heart activity. On the other hand, the 12-lead ECG machine, or also known as the standard ECG machine, has 10 electrodes and often used in hospital for various purposes. It can provide a comprehensive view of heart activity but takes longer time to set up. Moreover, this ECG machine can provide 12 distinct electrical views derived from the positioning of the 10 electrodes. Hence, it is called 12-lead ECG despite that it has only 10 electrodes. Lastly, I would like to discuss about the future use of ECG. In 2020, Liu and Lu successfully developed a machine learning algorithm capable of analyzing ECG signals to predict cardiovascular diseases. This technique achieved an accuracy of 90.9% and a specificity of 95.8%. With this technological breakthrough, patients identified as at risk can take preventive measures to avoid onset of these diseases.
Hi, I'm Kah Poh, and I will be explaining about the background of the project. Before we move on to the ECG parts, let us have some brief info about the output of ECG, the ECG signal. In the figure shown, what can be observed are the waves. P wave represent the atrial depolarization, QRS complex represent the rapid ventricular depolarization, while T wave represent the ventricular repolarization of the heart. Going on to the 3-lead ECG, which is the ECG that we will construct in this project. The 3-lead ECG was invented by Willem Einthoven, who was a Dutch medical doctor and physiologist. 3-lead ECG is commonly used for basic heart monitoring such as in the emergency or portable ECG. Einthoven records electrical activity of the heart by measuring the voltage between the right and left arms, which is the lead 1, the right arm and left leg, which is lead 2, and the left arm and left leg, which is lead 3. These form an arrangement which nowadays called Einthoven's triangle, which is shown in the figures.
Next, we will move on to the methodology of this project. The first step is to draw the schematic circuit in the Simulink and Stina software and configure them. The second step is to finalize the circuit, and then after we finalize the circuit, we will go to the medical electronic lab to do the prototype building, and then we need to test the prototype, and then we need to display the ECG signal in the graphical user interface in the Arduino, and then for the last one, we need to break down the cost for this project. In this project, we explore the process of creating and optimizing an ECG signal acquisition system using the TINA software. We will focus on 3 critical components of the circuit, which is the instrumentation amplifier, the right leg driver circuit, and the filtering stages. These components are essential for acquiring clean and reliable ECG signals for medical monitoring and diagnostics. Let's begin with the instrumentation amplifier, a cornerstone of our circuit. We use the N8128 instrumentation amplifier. It is a high-performance amplifier designed specifically for the precision application, including this ECG system. Its main role in the ECG circuit is to amplify small differential signals while rejecting the common mode noise. This is crucial in biomedical application where the ECG signal is often weak and surrounded by various sources of interference. Okay, next, we have the right leg driver circuit. It is a critical component for improving the signal quality in the ECG system. The RLD circuit operates by stabilizing the body's potential reference, reducing the noise and also artifact that can affect the ECG signal. It achieves this by processing the common mode voltage from the ECG leads and feeding back to the body via the right leg electrode. This feedback loop enhances the circuit's common mode rejection ratio and resulting in a cleaner signal. In our design, the RLD circuit used the LM741 operational amplifiers, which are ideal for their low noise and high input impedance. The last main component involved is the filter. We use a filter to refine the signal to ensure it is clear and usable. The first filter that we use is the first order bypass filter. It is used to allow only the relevant frequency range of the signal. typically between the 0.5 Hz and 100 Hz. This filter removes the low frequency noise, such as the baseline winder, and also remove the high frequency noise, such as the power line interference or master artifact. And then the second filter that we use is the low pass filter. It will eliminate the high frequency noise above the cut-off frequency, which is around 100 Hz.
Okay, let us have a look at the preliminary circuits of the 3-lead ECG. This circuit consists of few components and parts, which are the instrumentation amplifier, the dual power supply, and the first-order bandpass filter. The labeled electrical noise power source will act as a simulated noise of the electrical noise which have a frequency of 50 Hz. The dual power supply will provide necessary voltage to the operational amplifier in the circuit, which are the INA128 and LM741. There are two main parts of the circuit, which are the instrumentation amplifier and the bandpass filter. First, I will talk about the instrumentation amplifier. The amplifier that we use for the instrumentation amplifier is INA128E. The function of the instrumentation amplifier is to amplify the weak ECG signal, which is typically in the range of milliwatts or microwatts. It also rejects the common mode noise such as 50 Hz noise from the electrical power source. Besides, the instrumentation amplifier and A128E have high input impedance that allow the ECG signal to remain intact for amplification and processing. We also have bandpass filter in our circuit. The bandpass filter is implemented in two stages, which is the high-pass filter and the low-pass filter. The component used in the high-pass filter is a 47 microfarad capacitor and 10 kilo ohm resistor. So the cutoff frequency of this filter will be 0.34 Hz. For the low-pass filter, the component that we use is a 100 nanofarad capacitor and a 100 kilo ohm resistor. So the cutoff frequency will be 15.92 Hz. Thus, the frequency range of the signal that is allowed to pass the filter is from 0.34 Hz to 15.92 Hz. The noise and artifact which is out of the range will be removed and prevented to be present in the ECG signal.
After many trials and circuit design, finally we have come to the finalized circuit. As you can see here in this circuit, we will use the low pass filter and also the first order bandpass filter that have been explained by my teammate, which is Kah Poh. So here I will explain more about the low pass filter. As we can see in the box, there's low pass filter before the ECG signal entering the amplification stage. This is because the low pass filter will eliminate high frequency noise above the cut-off frequency, which is around 100 Hz, and ensure that this ECG signal remain clean. And then this stage further refine the signal for display and analysis.
Hi, I'm Jing Yee. I will continue to present the preliminary and finalized results. These are the preliminary designs consisting of the first self-designed circuit by our group member Darren, and also the simplified circuit as shown in the second design on the right. However, due to several reasons such as the complexity, cost consideration, and difficulty in capturing ECG signal, we decided to focus on the second design. Hence, before we proceed to build the circuit, we have simulated our preliminary circuit on TINA TI simulation tool, and this is the result that we got. Next on the left is the circuit we have successfully constructed, and it is exactly the one we used for testing. The first preliminary result we have obtained is shown on the right. The circuit successfully captured ECG signals, but several challenges were observed. The signal contained significant noise from surrounding equipment and muscle artifacts, and amplification is needed for better visualization of PQRST waves. After refining the circuit design by adding a filter, this is a simulation result we got. So next, we proceed to build the circuit, and this is the exact circuit that we used in the lab for testing. Finally, the finalized results show cleaner ECG signals with reduced noise and interference. To verify how accurate these experimental results are versus the actual results, we have our subjects wearing a smartwatch that is used to detect the heartbeat while testing is conducted. The heart rate was determined using the peak-to-peak frequency from the experimental results. To evaluate the accuracy of the measured heart rate compared to the experimental value, the percentage of error was calculated. The final calculated heart rate is 77.94 BPM, with a minimal percentage of error of only 0.077%, indicating high accuracy in the ECG detection circuit. This result confirms that the circuit is effective in capturing and processing ECG signals with negligible deviation from the expected values. Thank you.
Assalamualaikum and hi. So my name is Sauqi. I'm going to continue with discussion part. So our process design begin with simulations by MATLAB Simulink and also TNTI software. So the design for the first prototype, which is preliminary design, while it is functional, it was too complex and noisy. So after consulting with Dr. Yazid, we developed a simpler and cost-effective second design. So therefore, from this design, some adjustment can be made to acquire clearer signal. Now we are moving to circuit section and components. So basically, as you can see here, on the left side is preliminary design and on the right side is our final design. So both circuits has four sections, which is input, amplification, filtering, and output. This is what I have classified. So the INA128E instrumentation amplifiers provide a gain of 51, while the filters eliminate baseline drift and high frequency noise. So the final design signal is sent to the GUI, which is the oscillator via the LM 741, which is the op amp. And for the final design, we add another low pass filter to remove the extensive noise in the early stage. So this eventually cause the clearer output display at the oscillator. Here, heart rate was calculated from the peak to peak frequency of 1.299 Hz and resulting in 77.94 calculation of beat per minute with an error margin of just only 0.077%. So the system actually demonstrated exceptional accuracy of ECG signal acquisition. There were some challenges faced by our group during the construction of this circuit. So the challenges included the noise interference problem. For example, 50 Hz interference from the nearby electronics and also skin impedance. Therefore, applying low pass filter and also band pass filter can help to attenuate this noise. Poor electrode to skin contact also contribute to the signal acquisition problem. Therefore, applying new prep gel to the patient's skin before applying the electrode help to solve this problem and also can reduce the impedance. Lastly, the unavailable signal detection can be mitigated by verifying the components with a multimeter to help ensure the components continuity. For future improvements, it is suggested to improve in terms of electrode preparation. For example, use alcohol wipes before applying new prep onto the patient's skin. Furthermore, use higher order filters for better noise reduction. And lastly, conduct the tests in the interference-free environments. So this step will further optimize the signal accuracy of ECG.
In conclusion, our group designed a electrocardiogram machine to detect biopotential signals from electrical activity of heart by attaching electrode on the left and right arms and left leg of the subject. Besides that, the main components of our design consist of instrumentation amplifier to compare detected signals, passive and active low-pass filters to remove high-frequency noises. Moreover, resistors and capacitors are used along with the other components to adjust gains of the amplifier and cutoff frequency of the filters, while DC power supply is used to supply DC power to the amplifiers. Finally, our testing result proves that our ECG design is able to detect heart rate at very high accuracy. However, the improved design eliminated more noise compared to the preliminary design, but the plotted ECG graph still showed the presence of noise and we cannot see a relatively perfect PQRST waves. Furthermore, this device can only be used for simple heart rate measurement because it has only one lead. Thank you for listening, and this is all from us.